Welcome back, everybody. Welcome back to C++, parallel C++ for scientific applications. Well, last time we started to talk about some problems or some issues related to parallelization in general. I introduced some conceptual terminology, some concepts, and I tried to give you some hint at where the actual problems are when parallelization happens on a conceptual level. What I want to do today is to start looking into how we can implement how we can implement parallel programming models in C++. What facilities do we have available for that? That will continue the next 2 lectures, 3 lectures perhaps, where I want to introduce various programming models and what facilities we have available. Also today I want to talk about how threads, threads is kind of the basic thing I want to talk about today, but how we can synchronize between threads, what facilities we have to do that. Okay, so let's get going. Threads and synchronization. There we go. But as always, just to have some practical application for that and to give you some sense of why do we do that and have some real example for it, I want to look at yet another way to approximate the value of pi numerically. We have done that with Monte Carlo methods. Today we will look at approximating pi using numerical integration. And also, as always, let's start with some math background, just to put everything on a solid basis for everybody to understand what we're talking about. So I will introduce some numerical techniques for computing integrals by looking at variations on what's called Riemann sums. And I will briefly look at the Simpson's rule, which can be used to do numerical integration as well. We all know that the integral of a function f of x in a certain interval from a to b is defined as the area under the function. So essentially the area between the function and the x-axis. The notation is integral a to b of that function x dx, and we will try to find a way to approximate that and to calculate that area numerically. Since we want to do that in parallel, let's go back to our overall scheme of how we approach parallelization. And as we can see, the first step there, when we want to solve a problem, we have to think about some discretization and decomposition methodology. So let's have a look at that. Riemann, a mathematician from the 19th century, he introduced that definition, and the so-called Riemann sums are named after him. A Riemann sum is obtained by choosing endpoints in between a and b on the x-axis, where the points are increasing, so they are strictly ordered. And then if we take the sum of the values of our function x at the points of these x to x0 to xn and multiply that by the distance between the neighboring x values, then we get an approximation of that integral. So if you look at it this way, what we can do, we just have a certain interval. In between that interval, we have 1, 2, 3 points, and we calculate the area of the square defined by the width and the height, which is a function value. And if we increase the amount of intervals, so reduce the size of the intervals more and more, we can see that obviously the overall approximation of the area we get by summing up the areas of the rectangles will get closer and closer to the area we are looking for. So in the end, you can think of the integral as being the limit for delta x going towards 0 of the aforementioned sum. Fairly easy to understand, and I think it's a well-known way to calculate integrals. There are obviously different variations because nobody forces you to use the left-hand side of those rectangles. You can use the right-hand side of the rectangles. You can use the middle between the points and so on. So let's have a look at some of those variations. So if you divide our AB interval into n equal subintervals of the width dx, delta x, then the partition points are obviously a plus delta x, plus 2 delta x, and so on until we get to b. The left rule in the Riemann sums is then defined as using the value of f at the left edge of the rectangle. Nothing surprising there. There's a right rule where you do the same thing except that you use the right edge of the rectangle. You can use the midpoint rule where you just take the average of the two values between the left and the right edge of the rectangles, or you can apply some trapezoidal rule where you approximate the area underneath the function, not with a rectangle but with a trapezoid. You can derive these formulas yourself. They are really kind of self-evident. Okay. The other thing what we can do, I will not do that today, but it might be useful in your career if you want to calculate a multidimensional integral. You can do the very same thing for multidimensional functions. So if you have a n-dimensional function, the function depending on n independent variables, then we can compute the volume under that function in the same way by discretizing the space along the axis of the independent variables in pieces, which gives us some n-dimensional volumes, and we calculate those volumes, compute those volumes in the same way as we computed the areas underneath the function and sum them up, which gives us the overall integral, obviously. So we can generalize the Riemann sums for functions over domains of more than one dimension easily. An exercise, as always, some people ask me for additional work. Why don't you compute the left and right Riemann sums for y equals sine x on two intervals for an increasing number of subintervals, compare the results with the correct results, and so on and so on. So there are plenty of things you can do just to experiment with it, to write some code, to apply left, right, or trapezoidal rules. So feel free to play with that. A short word about the Simpson rule. The Simpson's rule is named after another mathematician from the 18th century. That's why I don't have a picture of him, but I have a picture of the book where he published that. Thomas Simpson. There are many variations of the Simpson rule, but I want to show you just one, which relies on approximating the function in between 2 points using some higher dimensional polynomials. And in this case, I will show you the formula you can use when you approximate it with a quadratic function. So for n subintervals, we got this formula where we have a sum, which is, by the way, called the 1/3 rule, 1/3 rule, because we divide it by 3. If you convert that into a sequence of sums, you get that formula. Again, I'm not going to derive that. This is quite self-evident if you try to do the math yourself. Another exercise, do the same thing as before, just use the Simpson's rule for that and see whether you get better results or not. Okay, that's kind of the theory behind it. Let's get back to what I want to look at today, namely approximating the value of pi by numerically integrating the function 4/1 plus x squared on the interval between 0 and 1, which gives us pi. So essentially pi is defined or can be computed as the integral from 0 to 1 over that given function. The function itself looks like this. So if you get the area underneath that function, you get the value of pi. Again, very simple to derive. Look at various sources in the internet. If you don't believe that this is true, you can easily derive that. So how do we do that? Let's have a look at it. Let's apply Riemann sums and define some squares, some rectangles underneath that function, where the area of each of those rectangles is defined by the width, which is h, and let's assume the width of all rectangles is the same, multiplied by the value of the function at the point of where the rectangle ends, which gives us 4 over I times h squared, right? The actual formula was 1 plus x squared, and I times h gives us the x value. If we plug that into our formula, we get the area of one of those rectangles just fine. So this gives us, for instance, the area of the rectangle I. Nothing surprising there. In other words, we can approximate pi by taking the sum of all of these rectangles from I going from 0 to n minus 1, where n is the number of rectangles we want to create. And h is defined by the number of rectangles. It's just 1 over n, essentially. Okay. Let's write code. Well, the code is trivial, as you can see. It's really just a loop that goes over n segments of x, and for each of the segments it plugs in the formula I had on the previous slide, h times 4 over 1 plus I times h squared. That should give us pi. Easy as that. No surprises there. We want to parallelize things. So how do we do that? Well, the first thing, as I said, is we have to figure out how can we decompose our problem after discretizing that. Well, we discretized it. Now we need to decompose it into smaller pieces that we can possibly run independently in parallel on different computing on different cores. We obviously see that the partial sums are all independent. So there is definitely a way to split that up and say, okay, I will run 3 of those on one core, 3 of those on the next core, and so on and so on. So we can compute the sum concurrently by building these partial sums over a number of blocks, well, which is in this case m, and we let go k from 0 to m and compute the partial sums over part of that integral. Again, nothing surprising there, kind of self-evident. So if we plug that back into the formula, what we get is a double sum, right? The inner sum goes over the rectangles for one of those partitions, for one of those partial sums, and then we have an outer sum which sums up all the values we collected for each of those partitions and multiply by h as before, and that should give us pi. Okay. Let's write the code for this. Still the sequential solution, but this time I deliberately split that into 2 loops. So we have an outer loop which goes over the set of partitions, and the inner loop goes over each of the partitions itself, where each of the inner loops calculates its own partial pi and adds up that pi to the overall pi after the inner loop has finished computing. Same thing as before, shouldn't be any surprising in any way for you. Okay, so what have we done? We have taken that function, we have split it into pieces, something like this, and we have said, we split it into pieces, and we now, instead of computing one integral, we are computing 4 integrals, where the first integral goes from 0 to 125 to 0.5, and so on and so on. In other words, if we summarize what we have 4 independent tasks, 4 independent sums, where each of the sum goes over the rectangles for each of those subsections we defined before. Okay, so let's put that into code again. And if you think about it, essentially what we can do now is we can have 4 independent loops, where each of the loops goes over different boundaries, right? The first one starts at 0, goes to n over 4, and the last one starts at 3 over 4n and goes up to n. The interesting thing is that you really run the same code for each of those partitions. So we have decomposed our problem very nicely. We have even some understanding how the code would like, and we know what we can run concurrently, because these 4 loops could run concurrently and we still would get the proper result. The question is, how do we do that? Well, the easiest way is to do it this way, right? Just have a main program where we run the 4 loops independently, one after another. The first one does the first sum, second one the second sum, and the last one obviously calculates the last sum of the 4 partitions. Again, no surprises. What we could do is to run these loops independently. So you could somehow think of them as being separate tasks, where each of the tasks has its own set of registers, its own stack, its own code it executes, and each of those pieces can run on its own instance of a task or of a thread, as we will see. Completely logical. And that kind of gives you the sense that where we're aiming at. What we want to do is to run these 4 loops in 4 separate threads in our code and make sure that these threads run concurrently, so that we can utilize 4 cores in this case at the same time, and possibly and hopefully speed up our computation of pi by a factor of 4. And we will see how far we can get today during the lecture. But before we go ahead with computing pi, I want to introduce you to the notion of threads, and especially how we can represent threads in C++ code, and what facilities does a standard give us, what other facilities we have possibly available to us. So the first question, what is a thread? What is a thread? Anybody? How would you, I mean, we have a kind of a gut feeling for what a thread is, right? We run code, we do things, but what is the definition of a thread? How would you define a thread? Anybody? Sam?
Were you picking on me?
Oh, wow. You're always smiling, so why not?
I would say a sequential, like something that executes processes sequentially.
Okay. Okay. Good. Other things we could add to that? So a sequence of operations, right? That's what you're referring to, and that's absolutely a thread. What else? Has anybody read the standard, C++ standard? What the standard has to say about a thread? Well, the C++ standard said a thread of execution is a single flow of control within a program. So you're quite close to that. I added a link here, so you can go there, look at the standard, how they define a thread. But there is more. There is a type which in the standard defines, which is did thread, and it says it is specified as a component that can be used to create and manage threads. So what we have kind of a vague understanding what is a thread of execution, and we have at least one facility that allows us to represent a thread in C++ code, which is that did thread type, and we will see how to use it in a minute. Just for the sake of it, the standard introduces another term which is somehow related, which is execution agent. And execution agent is a bit more general than a thread, because a stitch thread is explicitly defined as something representing an operating system thread. So something that the operating system manages, a P thread. Whereas a execution agent is a entity such as a thread that may perform work in parallel with other execution agents. And this will come to pass when we start talking about HPX a bit more, because HPX works with execution agents and not with threads. But we will get there. But let's get back to defining the notion of a thread a bit more concrete. What is a thread? Well, I say it exposes 4 properties. What are the properties of a thread? Threads. Well, one we already said, right? It's a sequence of opcodes that define a thread.
We need to control that flow.
Well, single flow of control, yeah. Okay, what else? Any idea?
Resources, like registers.
Very good. It's a set of resources, registers, stack, thread local variables, right? You're looking into thread local variables. So thread local variables are part of what a thread is defined. What else? If you have an flow of control, what is important to know when we look at the flow of the execution sequence? Well, that's a bit beyond threads, but what's important is to understand what's the next operation we want to execute, right? This is kind of where the thread is currently running. As you said, this set of registers, obviously, so the associated execution context. But last but not least, there's one more thing people don't think about, because a thread is also defined by its state. Namely, is it initialized, is it pending, is it running, is it terminated, this kind of thing. So just to understand what state is that thread in. So these 4 properties define what a thread is. Okay, how does C++ represent threads? As I said, there's a type stitch thread, and the constructor of a thread takes a bunch of arguments. The first argument is an arbitrary function. That function is the one that the thread is supposed to run. So when the thread is created, this is a function this thread will execute. And you have a means of passing along some arguments to that function. So you can say f1234, and 1234 will be passed to the function when the thread starts running. And will be used as the arguments to that function. So once I construct T, it represents a new instance representing a thread that executes f with the arguments with args as its argument. The thing to note is that if f exits, if f returns, finishes running, the thread is implicitly terminated. So it's kind of f is defining the lifetime of the thread. It's defining the flow of execution that thread represents. A second type C++ gives us, and it's called JThread. Don't get your hopes up. It doesn't mean Java threads. It means joining threads. And the only difference between JThreads and threads is that the destructor of JThreads joins implicitly. So when you destroy a JThread, it will wait for the thread to terminate. It will join with the thread. So it's kind of a convenience addition that makes working with threads a bit easier in some contexts. And we will use it kind of interchangeably during this lecture today. Both threads and JThreads have a member function which is join, which the calling thread will wait for the target thread to terminate and only returns after that. So you can wait explicitly for another thread to finish executing, essentially. If the target thread already has finished running, join doesn't do anything. It returns right away. Okay, some example. I'll create one thread, a JThread in this context. That's why its destructor will automatically join whenever that thread goes out of scope. It will wait. So main will not exit before the thread is finished running. The thread function is defined here. What I just do is, as you can see, I'm passing one argument to the constructor, which means this first thread will launch the thread function by passing a 1 as its argument to the function. And what that function does, it prints 4 things. It prints the number of the thread, It prints the address of the thread of the argument, and we will see in a moment why that is important, or what can be shown by that. It will show the address of a shared int, which lives in global space, global namespace, and it will increment the shared variable and print the value of the incremented int as well, just to demonstrate certain things. Now, why limit ourselves with one thread? Why not just, well, let's start 4 of those. And as you can see, each of those threads will start that function just passing a different argument to it. So we have in the end 4 additional threads being launched. All of those threads run that thread function, and each of the threads passes a different value of the argument to the thread function. This is what is printed. So as you see, it prints the argument value. Oh, okay, sorry. I passed the wrong arguments here. It actually prints 0, 1, 2, 3, so we should change these values. It prints the address of the argument, which in some sense is an address into the stack of that thread. And I am printing it here just to demonstrate that each of the threads gets its own stack. Okay, so each of the threads is completely independent of the execution of any other thread. The address of the shared variable is the same, as you can see. So all threads refer to the same variable physically. And since we increment that shared variable, each of the threads will give us a different value printed for that shared value. Okay. Interesting to note is that in this case, thread 3 actually prints 4701. And thread 0 prints 4703. So as you can see, there's no relation between the execution of these threads because they are kind of randomly are being scheduled by the operating system in random order. So anything can happen. So let's answer some questions about that. How many threads are in this program overall? Anybody? 5, right. Does the main thread join with the threads in the same order that they were created? Right, we create 4 threads, and then they are being joined implicitly by the destructors of the J threads. Is the join operation happening in the same order as the creation of the threads? No? Why not? Well, variables are destructed in the opposite order they are created, right? So the join operation will happen in the opposite order than they were created. Do the threads exit in the same order they were created? So do they terminate themselves in the same order they were created? No, they can terminate in any order, right? One thread can run to completion before the other threads even start running. It's just that the join operation will happen in a certain order, but the termination of the functions is not guaranteed to be in the same order. So if you run it again, will we see the same result? Probably not. We will probably see completely different values for the thread number associated with the incremented shared value, obviously, because we don't know in what sequence these threads are being executed. This gives you kind of a sense of that threads run completely independent of each other. So they can happen in any order, anything. There is no predefined sequence of things. And if we want to achieve certain sequencing, we have to do synchronization, and we will talk about that in a minute. Okay, so let's do another example. Let's say I have a very simple function, say hello, which receives a thread number again, and prints its thread number. And what this code is doing, it just creates 16 of those threads by passing a different argument to each of those, and then joins with all the threads explicitly afterwards. I'm showing this code just to kind of highlight the difference between a thread and what we can think of as a task. A task is really some functional unit of work we want to perform, whereas a thread is the underlying mechanism that helps us run that functional unit of work. So in this case, you can think of that function that I use to execute on the threads as being these functional work the task I want to perform. And the thread itself is that operating system facility that is encapsulated by the std thread type. By the way, same code, just with a JThread, looks almost the same. The only difference is that I don't have to join, because the join operation is implicit at the point when these JThreads are being destroyed, namely at the closing brace of the block where the object is defined. This is pure C++ semantics again, right? We rely on the C++ semantics that objects go automatically out of scope at the closing brace of the block where they are being defined. Makes kind of sense. Okay, so let's get back to our calculation of pi. I just encapsulated the code we had in a function that is called calculate partial pi, which now receives two arguments: the begin and the end of the loop iteration we want to perform, and it does a computation of pi, and we just assume that h is available somehow magically through a global variable or something like that at this point. So if we look at how can we run this function in a new thread, well, it's some straightforward code. The crux is here in this loop. We want to run as many threads as we have intervals, as we have blocks of work. So there are two questions. Well, first, you note that the thread functions always return void. There's no way to return anything from that function, because there's no way to get to that result value, because it happens on a completely different time scale compared to the main thread. So we can't just return the partial pi here. That doesn't work. How do we do that? The other question is, how do we get the partial sums there? Because we want to somehow collect that overall pi based on the partial results. So let's try to solve that issue, and I'll show you how you can do that. What I do here is I extended the argument list. I'm passing the h in this time. That doesn't make any significant difference. But the trick is that there's an additional argument which represents that global pi we want to collect. And I'm passing it in by reference, because each of the threads has to update that pi value as it finishes. So how would the code look like? I now create a vector of threads, and I create each of the threads by passing the function, the begin and end. That parenthesis is superfluous. I have to remove that. H, and please note the special syntax I'm using here. stdref. Why do I have to do that? Is it clear to anybody? Why do I have to specifically tell the thread that this argument is a reference? Can anybody think of that? Nope. Yes?
You can't just pass in pi, because pi is a double, so it could be confused with.
Well, you could pass in pi, but what would happen if you were just passing pi in here?
I treat it as a pointer.
No, it would pass in pi. Everything would be fine. It would compile. You would get a reference to the pi. But it wouldn't refer to the global pi anymore, but it would refer to a local copy of the pi which is stored in the thread. Right? When you create the thread, it has to copy all the arguments in order to, at some point later, be able to pass these arguments to the thread function. So std_thread will copy all the arguments into some magic place and will use those values when the calculate partial pi is being invoked. So everything would compile, but this pi would refer to that local copy of that pi, which is inside that thread object, and we wouldn't see the overall sum. So this is kind of a tricky piece, and I want to highlight that because you might run into these issues, that in cases when you want to pass a reference from the main thread to the launch thread, you have to explicitly tell the thread, hey, this is a reference. Please treat that as a reference. Don't copy that thing internally, but pass along the address of my variable. Okay? might happen to you at some point. So it's a general problem in when you start these threading, when you start writing multi-threaded code, because you don't know when things are actually happening. And when you're passing references from one thread to another, you have to be very careful, A, to make sure that this variable doesn't go out of scope before the thread ends. That's why I have these joins explicitly here before I print the pi. So you have to be on the lookout for this particular issue. Okay, so let's have a look. So we have that partial pi variable, which is a local variable. Everything's fine there. And we have that double reference pi, which is a shared variable. And when we add the partial pi to the pi, we update a shared variable. And we have seen before what happens when you have several threads working with the same shared variable. Well, the overall code looks like this. Now I'm just, instead of having a loop, I have it explicitly written there so that we can see it better. So we have now create 4 tasks. Each of those tasks is run by one of the threads. But the issue is that each of those tasks has its own, works with the same variable that is somewhere in the shared memory. So we have to deal with the issue that all threads concurrently try to update that pi. And as you might guess, this is a race condition. We will not see the proper result, because what's happening is that each of the threads has its own set of registers. And this pi is certainly loaded into the registers. So the update of pi will happen in the registers, and only after that the pi is written back to its memory location. The other thread is doing that as well. So one thread might overwrite the value that the other thread has stored in the shared variable before. So what we need is some way to synchronize, and I think we talked about that at some point already. There is a notion of a standard mutex, which is a way to prevent multiple threads of executing a certain piece of code, to create a critical section which guarantees that only one thread executes that code. A mutex is an object which has 2 operations, lock and unlock. But unfortunately, mutexes are very prone to deadlocks if you're not very careful. And just to give you the 2 problems we have and the solutions to that, the first problem is if you lock a mutex and never unlock it, then this will lead to a deadlock, because other threads will never be able to make progress beyond that mutex. The other problem is that if you have more than one mutex, that have to be acquired in order to do a certain operation, then you have to make sure that all threads and all code acquires the mutexes in the same order of acquisition. Because if you change the order these mutexes are being acquired on different threads, you will run into deadlocks as well. And one facility to avoid the first problem, that things are never left locked, is the lockart, which when created takes the ownership of the mutex, and when destroyed, when it leaves the scope, definitely and guaranteed releases the mutex. And the other one, and we will not elaborate on that, is a facility in the standard which is called standard lock, which allows you to guarantee that the sequence of acquisition of several locks is always the same, and you will never run into deadlocks there. Okay, so what we do, we define a mutex, and we say, okay, we protect the update of pi with a critical section. It's a mutual exclusion region, and everything between the lock and the unlock of the mutex is guaranteed to be executed by one thread at a time only. So we should be okay. So what we get is when we run without the mutex, we get a wrong result as predicted, because one thread probably has overwritten a accumulated value that the other thread has provided. But the overall execution time is quite fast. So let's assume it's a fast execution with 50 milliseconds. But when we add the mutex, we suddenly get the correct result. Yay, great. So we achieved what we wanted. But our code suddenly runs, I don't know, 60 times slower than before. It's almost 70 times slower as before. I think we talked about that in previous lectures, why that's happening. The reason is that the constant locking and unlocking of the mutex just blocks progress. And since that's happening on many threads at the same time, we have a lot of contention, which slows down things. And in the end, sequentializes the computation, right? Because only one thread can do the computation at a certain point in time. One way to solve it is to not lock and unlock inside the loop, but lock and unlock once inside the function. Okay, what do we get? Well, without the mutex, it's still wrong. With the mutex, it's faster than before. Yay! Look, we almost we got much closer to the non-protected version of the code, and we get the correct result. Might be a solution, but I doubt it is, because we will see in a moment that this doesn't solve our problem completely. Another problem, as a side note, I just, for the sake of it, increased the number of oval intervals to 1 billion. And now I get a pi which is around 12 point something. Anybody why that's happening? Any idea? I accidentally ran into that, so I thought I'd show you in the lecture.
Is it overflowing?
Correct. Well, look, we have an integer here. So it's simply overflowing. As an aside, C++ has a bunch of integral types that have certain sizes predefined. But since those sizes are not really well defined, they are kind of just saying, okay, a long has to be at least as large as an integer, and an integer has to be at least as large as a short, and so on. I thought to write a short program which actually prints information about various types. And I'm printing the information for all the integral types I could think of, including the floating point types. What it prints is the number of bytes, the number of bits, the minimal representable value, and the largest representable value for each of those things. And what we get is this. So as we see, as long as we use integers, the largest number we can represent is 2 billion. And our computation just overflowed. And that's why we got the wrong results. So what can we do? Well, the solution is simple. Instead of using integers, we just tell the compiler to explicitly use 64-bit integers. And then things suddenly start working properly. And we get the proper pi. And this time, obviously, a bit larger, bit longer, took a bit longer to compute because I have many more intervals. But as I said, this is not the solution, because if we compare it, the execution time when we run this code on 4 threads with the execution time when we run the same code with just 1 thread, we see that the speed up is minimal. So we don't gain anything from actually parallelizing things. Can anybody tell me what's happening? Why isn't the multi-threaded version with 4 threads or with 10 threads not speeding up things compared to the sequential version? Anybody? We have protected pi now, right? We get the correct result. Yes?
There's only one loop that will execute at a time.
Right. Correct. What we have is, well, we found concurrency, we fixed it. We had a race, we fixed it. It was too slow. We tried to fix it. But what we have now is that each of those loops kind of is sequentialized, because there's a mutex around the loop, right? Only one thread can execute the loop at a time. So only when the first thread is done with a loop, the second thread can actually start computing things, which sequentializes our execution again. So we're back to where we started. Bummer. What is the solution? Anybody? What would you do? I don't want to put you on the spot again, so but do you have a solution?
You could use the mutex just when you're updating the global file.
Yes. You just have a local pi, and once you have calculated your local pi, you grab the mutex only for a very short amount of time when you actually update the global pi. Very good. That's exactly what the actual solution is. Okay, so we found the solution. Things work. We really get good speed up. Things are parallelizing very well. And now this is our mutual exclusion region, which is very small because all it does, it adds two doubles. This is just a piece of code that allows us to control the number of threads, just for your reference. If you want to have a look at that, nothing special there. So now we see the results that when we increase the number of threads, 1, 2, 4, 6, 8, we actually get a certain speed up. And we don't get a lot of speed up later beyond 6 cores because my laptop has only 8 cores. And things just flattened off. There was no way to utilize all the concurrency there. But we get reasonably nice speed up numbers. Things seem to work well. Good. Yay, we calculated pi. How about that? Now let's talk about how we can make that locking safer. Well, in this case, nothing bad can happen. But imagine you have some code inside the lock read, inside the critical section that actually throws an exception for whatever reason. Throwing an exception means that the code will exit from here and will jump somewhere completely else to the point where the exception might be handled. And that means that in the case of an exception, the unlock would never have been called, which will lead to deadlocks. So no future no other thread that tries to call mutex lock will succeed because the mutex is still locked, right? There's no way, so you will see a deadlock. As I said, there is a facility in the standard that allows us to avoid that. It's called lockguard, and what you do, you construct a lockguard at the point when you want to lock the mutex, and it will acquire the mutex, and whenever the lockguard goes out of scope at the closing brace, it will automatically unlock the mutex, will give the mutex back, and that's guaranteed. So even if inside the critical section we have an exception, that exception will still call the destructor of the lockguard and will make sure that the mutex never stays locked, no matter what happens. So the rule I want to convey is never use explicit lock and unlock in C++ code. Never do that. Always, when you have to acquire a mutex, always use either lockguard or unique lock. There are different facilities that are available, and that guarantee that there are no deadlocks in the code caused by not unlocking the mutex at some point. Okay? Again, this is one of the big benefits of C++. You have the guarantee that a destructor of an object is called no matter what, under all circumstances. So if you are in the interview at a company for a C++ job, and the guys ask you, what is the most important facility in C++ for you? There's only one answer you can give. And that answer is, I think I gave you the answer already, right? That answer is the destructor. And if you say that, then you are hired, because they will understand that you understand what C++ is. The destructor is one of the most important facilities C++ has, even if it's not visible and is not invoked visibly anywhere. It's just the compiler guarantees that the destructor is always called when an object goes out of scope, no matter what way, exception, exit of the scope of the execution or whatever, it's always destroyed, okay? Okay, so let's get back to our example. By the way, we had a shared variable there as well, our shared integer. And if you put a std lockguard around it, we even guarantee that there's no scrambling of the output, because otherwise the output might get even scrambled, right? Because when several threads try to write to the output to standard out, the sequences of characters might get scrambled, and you might not see the nice one line per thread output anymore. So I included that print statement inside my critical section here, just to guarantee that the output is proper. Okay, cool. What can we do with threads now? where can we go from here? Well, one application is what I showed you. And we have seen that while threads are nice and is kind of the basic facility to ensure things are being run concurrently, it's very difficult to use right. Starting with that std_ref, you have to pass under certain circumstances. You have to somehow funnel the result of the computation the thread produces back to the place where you actually need it. So it's difficult to manage. And my suggestion is, whenever you do parallel codes, never use std threads directly. No raw threads. Raw threads are evil and very difficult to reason about. Even more if you have 1 million of those flying around in your code, so you will not be able to reason about that anymore. Because a thread is it's almost like a pointer, right? You don't want to use a pointer because you don't know what's actually doing. Thread is very similar. Don't use threads. For that reason, let's have a look at how can we use these threads, or how are threads being used in higher level APIs and facilities, like that parallel for each we have looked at before. And I want to show you how we can implement our own parallel for each, just based on the knowledge we have so far. And we can go surprisingly far with that. So what is a for each? Well, a for each is essentially you have a sequence of elements, and you have a vector which stores those elements, and then you call for each, which is an algorithm that will invoke the given function for each of the elements in the sequence between begin and end. Easy as that. And this is still the sequential version, right? So how is that implemented? Well, it's implemented in a very simple way. And as you see, the std for each algorithm is just nothing more than a glorified for loop. Because what it does, it repeats the invocation of f with the current dereferenced result from our iterator b. So it starts with the iterator that points to the first element. When you dereference it, you get the 0, so you call f with 0. Then you increment b, which moves it to the next element, which is a 1, and you repeat that until b reaches the end of the sequence, and that's exactly what you want. So, yay, glorified loops. But wrapping glorified loops in algorithms makes things much more easy to reason about, because when you look at that code, if you have that while loop in your code, you have to think, what the hell is that doing? But if you have a statement which says std for each, then you immediately know what this is doing. You don't even have to think about it anymore. So it's a helper for us. Anyway, let's parallelize that. So let's go back to the standard, what the standard says. And the standard introduced so-called execution policies, which are called sec, par, unsec, and par unsec. Those are special objects, special predefined objects that can be passed as a first argument to our for each, or to any of the standard algorithms actually. Where these execution policies convey restrictions that are imposed by the body itself, by the lambda. Sec means the lambda I'm passing to you has to be executed in order on the current thread, on the calling thread. So there's no way that the loop can parallelize things. Unsec means you're allowed to parallelize things, but please only on the calling thread. So essentially you are allowed to do vectorization. Par means you can execute it in any order of any thread, on any threads, no problem. So this allows to do parallelization, and par unsec is essentially just giving you the giving the implementation the ability to do both vectorization and parallelization at the same time. There is another execution policy we have already seen, that SIMD execution policy. I introduced that when we were talking about the Mandelbrot example. Just for the sake of it, I'm listing it here as well. And there are more, and we will see those. HPX introduces a bunch of other execution policies, but let's not talk about those at this point. Okay, so let's parallelize our loop. How does parallelization work? Well, parallelization does split our input sequence into chunks. It just says, okay, I want to parallelize that on a certain number of cores. So I assign a certain subsequence of each of those, of my main sequence to each of the cores, and let each of the cores deal with a subsequence of those and run those in parallel. The way I make that happen is by passing the std execution par argument as a first argument for each, and I will hope that for each is actually doing the parallelization. How is that implemented? Well, the implementation is straightforward, as you can think of already. I have a for each which takes the parallel execution policy type as its first argument. So this for each invocation will actually invoke this function. Otherwise, the other arguments are the same. The first thing I need to do, I need to find out how many elements do I actually have. And I do that by calling another algorithm which gives me the distance between B and E, which is the number of elements. I create a vector of threads because I need a bunch of threads, right? I want to run one thread per chunk. I have a loop which goes over the chunks. Let's say I have some magic knowledge how many of those chunks I actually need. So let's say it's 4 or something. And for each of the chunks, I create a new JThread object which first finds its begin and its end for a particular chunk, and then calls the sequential algorithm for that sequence of my overall sequence. The interesting thing is that, and that is probably true for all parallel algorithms, they chunk up the input into pieces and then invoke the sequential version of the algorithm on each of those pieces concurrently. So we don't even have to implement our own for each. We just use for each sequentially on a new subsequence, which is shorter than the main sequence. Please note that since I'm using JThreads, they will join automatically when they are being destroyed. So this is your parallel algorithm there. Yay. Yes?
Since we have seen that state vector allocates things on in exponential sizes,
Yeah.
does it mean that state vector will have, for example, if we only needed 70 Z threads, it will automatically create a size of 32?
It will probably allocate more memory, but this is an implementation detail of the vector. So yeah, we have what you can do before actually start adding things to the vector. You can resize it or reserve the amount of memory you actually need, and that avoids reallocation. I just have left that off because of, well, slideware, right? I want to minimize the code on the slide.
So it will also mean that those 32 Z threads are created?
No. A default constructed JThread doesn't do anything. That's why I push back a thread when you pass a function. Okay, a default constructed one doesn't do anything. Okay. Okay. So what observations do we have? Parallelization concurrently runs sequential operations on part of the input most of the time, at least for CPUs. On GPUs, we will see in the future that this might not be true because GPUs usually do use completely different parallelization schemes. But at least on the CPU parallelization, this is almost universally true. The other thing, which is not quite obvious, is that iterators for parallel loops should be random access. Why is that? Why should they be random access iterators? So why shouldn't I use a std list and pass it to a parallel algorithm? Anybody? What's the computational complexity of computing the distance between two iterators if the iterators are not random access? Right? The only operation the iterators support is +1. The only thing you can do, you can increment it by 1. So in order to get the distance between B and E, you have to repeatedly call +1 on B until it hits E in order to know how many elements I need. Right? So that means that for anything but random access iterators, this operation turns into a linear complexity operation, ON, which defeats the whole purpose of parallelization. because by the point you have computed the size, you have gone over the sequence once. So why not do the actual operation while going over the sequence? So the essence is, be aware that whenever you use parallel algorithms in C++, your iterators you're passing to the algorithm have to be random access. Otherwise, you will not get good performance. Or vice versa. If you're getting bad performance, one of the reasons could be that you're passing iterators that are not random access. The other thing is num chunks, as I said, is a magic number. Where do we get that from? How many chunks do we use? How many cores do we use? Other arguments, right? How do we define the association with tasks and cores? How do we make sure that these things run really concurrently? So all these things are additional problems that are not solved in the solution I gave you, but we will solve them during this course in the future. Okay, cool. What I want to do now is to give you the tools you will need to solve the next assignment. Okay, so listen up. The next assignment will be the midterm assignment, which I will publish on Monday, which gives you a week to solve the midterm and hand into midterm. And right afterwards, I will post a new assignment where you will need condition variables to solve it, because the tasks, one of the tasks in that assignment will require you to implement inter-thread communication and inter-thread synchronization. Okay, so besides mutexes, C++ gives you other synchronization facilities, and one of those is called the condition variable. It is used in cases where one thread has to wait for another thread in order to continue its work. So you have to wait for a certain event that happens in another thread in order to go forward. For example, when you have a producer-consumer thing, right? When you have a queue where one thread is adding things to the queue and another thread is pulling things from that queue. You have to inform the waiting thread that new data has arrived in the queue for the waiting thread to be able to pick it up, and so on. So the condition variable makes the calling thread wait until it is notified by another thread, and only at that point it will go ahead. It has three functions. A mutex has two functions, lock and unlock. A condition variable exposes three functionalities. One is wait, which causes the current thread to block until the condition variable is notified. Notify one, which makes one waiting thread come out of its wait, and notify all will wake up all the threads that happen to sit in a wait somewhere in order to go forward. So let's have a look at a small example. Let's assume I have an integer which I want to send from one thread to another thread. And one thread takes a while to produce that integer, and the other thread has to be notified when that integer has become available. So I have a producer which produces the integer and a consumer which will supposedly consume it. And I launch two threads, one that runs the consumer, one that runs the producer. And the consumer will have to wait for the integer to appear to be available in order to do its work. So let's have a look at these two functions, the producer and the consumer. Let's start with the consumer. In order to use a condition variable, and the condition variable is defined globally here, so just to be available to both threads. So in order to use a condition variable, wait, I have to first acquire a mutex and pass that mutex to wait. And we will see in a moment why that is necessary. The consumer does nothing more than waiting for the value to appear and then printing the value to the screen. So it doesn't know when that value will be available because it doesn't know when the producer will actually run. So it has to wait on the condition variable. As I said, I have to acquire the lock before calling wait. And what wait does, it does two things. It unlocks the lock and suspends the thread in an atomic fashion. So it is guaranteed that nothing can get in between the moment that lock will be unlocked inside wait and the point when the thread is being suspended. Now, when another thread calls notify, that lock is reacquired before the thread comes out of wait. So you can be sure that after the wait, the lock has been acquired again. The lambda I'm passing to wait is an additional condition which allows to check whether the data is actually available. Right? I had a Boolean here, data ready, which is initialized to false. So this thing will wait until notify is being called and the lambda returns false. So as long as lambda returns false, this will wait. Now let's have a look at the producer. The producer is very similar. I'm using the locker to protect my data because I don't want other threads to mess with the data. Then I print what data I'm going to send. And after I have set the data and have set my flag to true, I'm calling the notify1 on the condition variable, which makes the other thread come out of this wait so it can start working with that variable. So as you can see, the condition variable is a very convenient way to communicate between threads, to send one value to another thread, to notify one thread that something of an event that something has happened so that the other thread can go ahead. Any questions about that? No? Okay. What I wanted to do now, and that's the end of the lecture, is to mitigate one of the issues with creating threads. Creating a thread is a very, very costly operation. So when you create a thread, it takes milliseconds, up to milliseconds for the operating system to get to the point that the thread function is actually executed. So you don't want to create the thread whenever you need one. What you want to do is to have a facility which kind of creates a bunch of threads in the very beginning and then uses those threads to execute all the work you want to pass to that thread. And after the work has been executed, it goes back to sleep until new work happens, and then those threads are being used to execute that. Such a facility is called a thread pool. A thread pool, in its constructor, it creates a number of threads which will be put to sleep. They don't consume any resources. And then you start adding tasks to that thread pool and tell the thread pool, hey, run this, run this, run this, run this. And whenever new work appears, one of the threads that is sleeping is resumed, runs one of the tasks, and goes back to sleep. And that allows you to avoid to create a new thread for each of those tasks to be run, because resuming a thread is a very cheap operation. It's much faster than creating a new thread. So let's see how we can implement that. I'm creating a class which is called thread pool. What do we need? Well, we need a constructor which creates a thread pool with a given number of threads. I'm passing one argument to this thread pool constructor, which tells it how many threads should it create in its constructor. And if you don't specify any arguments, it will use as many threads as there are cores available in the system. So std thread hardware concurrency gives you the number of cores that the system has. So by default, if you just default construct a thread pool, it will create as many threads as you have cores. Might be what you want. We need a destructor. And for simplicity, what I will do, I define a destructor that actually stops the thread pool and will join with all the threads. So you create the thread pool, do all the work, and when the thread pool is going out of scope, you stop doing things. It's a very simple scheme. What we also need is a function which allows us to add another task to the thread pool. And please note, the type of the task is something we haven't seen. It's a std function of a void parenthesis. What does that mean? A std function is a facility that the standard provides you with that allows you to store any function that exposes this prototype. So it can store references to any function that returns void and doesn't take any arguments. Any functions. Could be a lambda, It could be a global function. It could be anything that exposes the prototype of not returning anything and not expecting any arguments. It's just a weird syntax that is being used here, so don't be confused by that. Read that as a std function that references a invocable that returns nothing and doesn't take any arguments. Okay? What members do we need? What do we need to store in our thread pool? Well, we need to store a vector of threads, obviously, right? We have to have them somewhere. We have to have a queue of tasks for those tasks that have been added so that these threads can pull from that queue and can start working. And that queue stores, obviously, things of that type. Our tasks are std function of void parentheses. We need a condition variable and a mutex in order to coordinate between the threads, in order to wake up threads. And we need a bool which tells us, hey, we are done running, stop the whole thing, go home. Okay? Any questions so far? No? Okay, let's implement those functions. And you will see that they are relatively easy to implement. Surprisingly easy, actually. Let's look at the constructor. Well, all the constructor does, it creates a bunch of JThreads with a thread function, where the thread function is defined here, and I will expand the thread function. You can think of the thread function as a while loop that is running infinitely and is trying to pull new tasks from the queue, executes the task, gets the next task from the queue, executes the task, and so on. So it's really just a loop that pulls things from the queue and executes them. So each of those threads will run this loop, which is exactly what we want, right? It will wait until a task appears, then it pulls the task from the queue, executes the task, goes back to sleep, and so on and so on. So let's have a look at this function. Well, let's say we want to pull the next task and we want to execute it at some point, right? This is a function which doesn't take any arguments, so I can invoke it by just not passing any arguments to it. I create a scope where I define a unique lock, and that scope is necessary to make sure that the scope is not, the mutex is not being locked while the task is being executed. So I want to unlock my mutex during the execution of the actual task. That's why I have that additional scope here, just to make sure that this unique lock goes out of scope at the right moment. Then, as I said, well, that thread goes to sleep. Go to sleep. And it will wait there as long as there are no tasks available and the thing has not been stopped. It will come out there only once tasks are available. When it comes out and it sees that it has been stopped and no tasks are available anymore, it will just exit. That's the end of it. And otherwise, it will pull the next task from our queue. We'll just say, okay, give me the next task, pop it from the queue, and that's it. So this is a whole loop. As I said, all it does, it waits for the next task to appear, gets the next task from the queue, and executes the task once it got a new one. That's all it does. Relatively easy to understand, I think. What about the enqueue function, which adds a new task to the queue? Well, you could write that yourself, I guess. All you have to do, you have to lock the mutex because you have to protect our queue. We push back the task onto the queue. And afterwards, once we have put the new task on the queue, we notify one of the waiting threads. So, okay, there's a new task, go ahead. I don't care which of those waiting, just the first one. And that's fine. Straightforward. Last but not least, the destructor. Well, the destructor, what it does, it grabs the lock to set our stop variable to true, to tell the pool to stop, and then it notifies all waiting threads. Because there could be more than one, it tells all the threads that are waiting, hey, please go ahead, come out of your wait, and either execute the remaining task if there's one, or just exit your loop. That's it. There you have a thread pool. By the way, you can use that for your homework if you want, if you think that is somehow useful. I have no problems with that. That's why I'm giving you that code. Just how to use it? Well, I create a thread pool with 4 threads. I have a loop which adds 50 tasks to the thread pool, and each of those tasks prints something and then goes for 100 milliseconds, goes to sleep for 100 milliseconds to pretend that it's doing some work. And that's it. And at the point when the thread pool goes out of scope, the thread pool, all threads will be stopped, and it will synchronize here and wait for all the 50 tasks to execute before actually exiting main, which is exactly what we want, right? Easy to use. The last thing I want to show you is how we can use that thread pool for our parallel loop. Because wouldn't it be cool if you didn't have to create the threads for each invocation of for each? We create it once, then we pass our thread pool to all our for each invocations, and we don't pay the cost of creating the threads and deleting the threads inside each of the for each, but we can use the same thread pool for all the for each invocations we have in our program. For that, I'm just passing a thread pool now with 4 threads, and the implementation is the same, almost the same as before, except that the argument now is a thread pool. And the difference is that instead of creating a new thread, I'm calling pool enqueue here to add the next chunk of work to my thread pool. The only thing that is additionally here, which I have not shown in the code before, you have to add a wait function, which makes sure that you exit the for each only after all the tasks that have been enqueued have finished working. Otherwise, you will change the semantics of for each, and there might be still things running, even if for each has exited. Cool. So, conclusions. Threads are the operating system unit of concurrency. It kind of abstracts a virtual core. You can think of it as a virtual core. You can use JThreads and other facilities to manage threads within a process. But I strongly suggest that you don't use threads directly. If you want to use something like threads, build these higher level facilities like thread pools or similar things on top of them and use those, because that allows you to reason about things. You don't care anymore how many threads are actually running, right? Even if you have 500 tasks, you just throw them at this thread pool. It will do things as you need it. And we talked about 2 synchronization primitives, mutex and condition variables. There are more in the C++ standard: semaphores, binary semaphores, counting semaphores, and so on and so on. And if you need something more sophisticated than condition variables, I urge you to read the documentation. You will find a lot of information about these additional synchronization primitives that might be useful in other contexts for you to use. Okay. Questions? Just on time. Thanks for your attention. I'll see you on Tuesday. Please note that I will post the midterm on Monday. You have exactly 1 week for the midterm, for the take-home midterm. So don't waste time and wait for the next lecture. Thank you.